Hello everyone, my name is Young Jae, and today I am going to talk about autonomous underwater environment, perceiving and modeling, an experimental campaign for forward-looking sonar-based automatic target recognition and data association. This work has been presented by Leonardo, Zacchini et al. This work has been published in IEEE Journal of Oceanic Engineering on April 2023. Let's prepare. Let's start our presentation. Here are the contents of my presentation. First, I'd like to introduce the notation of hydroacoustics. Hydroacoustic is divided into two words, hydro and acoustics. Hydro refers to water, and acoustic refer to sound waves. Therefore, hydroacoustics means sound waves in the water. They can be used in signal recording, sonar, or recording under seabeds. Autonomous vehicles are the integration of modern robotics and artificial intelligence. It senses its environment with sensors while navigating vehicle without or little human intervention. These images are the example of autonomous vehicle. Those vehicle reduces bottlenecks and optimizes traffic flow by technical advances. They can be also interpreted with 5 different factors: the connectivity, algorithm, mapping, safety, and sensors. Autonomous underwater vehicle refers to an autonomous vehicle in oceanic environment. They use sonars as sensors, such as side-scan sonar or forward-looking sonar. Most communications are done in sound, which are poor, and little or no global navigation satellite systems are provided. Therefore, connectivity needs to be improved when communicating with AUVs. Sonar is an abbreviational word from sound navigation and ranging. Side-scan sonar creates large areas with shadowgraph, as shown on the top right picture, and it primarily used for mapping large areas. It can scan the underwater vehicle's size and keel, and it generates high-resolution 2D images. The image on the bottom right side is a picture of side-scan sonar of sunk Akagi-class aircraft ship. Now, forward-looking sonar is used for real-time navigation and obstacle avoidance. It focuses directly ahead of the sonar platform and are used in hover navigation. However, shadow-based dataset for FLS has zero or low quality. Now, this paper focuses on improving the connectivity of AUV system with artificial intelligence. An automatic target recognition is improved with forward-looking sonar. We especially use those FLS images due to high resolution and stableness. We experimented with real objects of potential interest in the Italian basin. Now I'll talk about background concepts. Automatic target recognition solutions for 2 different kinds of vehicle, such as unmanned ground vehicle and underwater autonomous vehicle, are different. For example, unmanned ground vehicle has slightly distorted images of obstacles, and image analysis and object detection can be easily maintained with CNN or DNN solutions. The underwater autonomous vehicle, on the other hand, have very tough and high computational image data. Therefore, image analysis and object detection is hard to achieve. This is a graph of comparison between recognition system with normal convolutional neural network and recognition system with deep neural network. CNN is time-consuming and requires image load and has limited computing power. Also, recognition conditions are very high. Recognition system with DNN can improve their performance with transfer learning and data augmentation. This graph shows the conventional research on different template matching-based object recognition approach. This is the result with researches with CNN and MLP, which stand for convolutional neural network and multi-layer perception. Those show that accuracy and the parameters and the computational time with CNN and MLP. With the DNN solutions, there are several possibilities. For example, you only look once, or YOLO, has detected underwater in the diver, and the several advantages are shown, such as high frame rate. However, single-shot detector was tested on optical images and benefited high frame per second and compatibility. Region-based CNN are tested on underwater images and benefited high accuracy and low interference speed. To model the online environment, there are three required characteristics of ATR-based targets. First, we have to link the features to semantic objects. Then, we associate the data to semantic objects. With the mathematical model, we finally generate the online environment with the flow of the waves. Now we select our DNN model. The network requirements for AUV. First, because it is the experimental product, the model should not require thousands of images to be trained on a custom dataset. Therefore, backbone algorithm using pre-trained CNN weights are required. Also, acoustical frames are acquired at a low frame rate. For this case, 3 Hz in this work, and high interference rate is not required. However, network accuracy is the very most important and shall favor the interference speed. For the dataset, we have gathered 175 frames in a native solution of 894 for 77 pixels and containing one of or more detectable targets have been selected. The black and white image shown on the upper side is the one of the dataset. Now, with the possibility of DNN, we pick 2 possibilities. The chosen possibility is a single-shot detector and region-based CNN. For the training environment, for the RAM, processor, and GPU, we evaluated those SSD and region-based CNN. Successfully, those single-shot detector utilized the downscaling process and trained using RMS Pro. The batch size was 24. However, region-based CNN utilized low resolution and low frame. They utilized stochastic gradient descent with mask region with CNN and trained using RMS Pro. The batch size was 1. Therefore, both systems fulfill the training environment request. For additional online validation with the validated dataset, the preliminary qualitative analysis was processed with automatic target recognition. Therefore, we utilized the mass RCNN and SSD with those acquired data. The PC setting remains the same with additional validation. These are the results with Teledyne BlueView M900 main specification. As you can see, the CNN performance indicator shows that the mass RCNN Inception V2 has a high precision of 0.95. However, the SSD MobileNet V2 achieves 4 frames per second in this word. Because we use acoustic frames are acquired at low frame rate in this word, and high interference rate is not required. Therefore, we utilize the SSD MobileNet V2. For word modeling, we utilize a probabilistic multiple hypothesis anchoring algorithm. The PMHA fuses major advantages of multiple model techniques. The word objects are represented by anchors, which are updated over time. Specifically, an anchor alpha A is described as a tuple with time frame and k time frame object measurement with whole set of anchor behavior. As you can see, MAK is the whole set of anchor behavior models. First of the whole set anchor is the constant position model, which represents the stationary position of the anchor. Then the second random drift model represent the slight and unpredictable movements. The probability mass function associated with single behavior model can be presented with the known coordinates of stationary or moving target. The qualitative perspective can be experienced with likelihood of how well the new measurements fit with the predicted states and prior probability accounts for the likelihood of current measurements being associated with existing or new anchors or representing false detection. Posterior probability of parent hypothesis for past association and anchor states align well with the measurements received. Now, the PZK over P k minus 1 squared is a constant used to ensure that the sum of the probabilities over all possible hypotheses equals 1, making the computational valid for probability distribution. Now, with the data association method, we follow those 3 steps. First is the observation and measurement. The observation measurement is can be divided into 3 steps: observation, discovery, and measurement. Then, from the true state of nature, we build a tree. Each leaves are consisted of the hypotheses that are related to data association. Then, with the mathematical model, we model the world. For FLS, we supply the north-east-down frames, which are depicted on the right picture. Position estimate is represented using a multidimensional Gaussian density function with the mean centered at the NET reference position and the covariance defined as a 3D identity matrix, like here. For the experiment, this is the overall environment for our simulation and experiment. As you can see, autonomous buoy is connected to workstation with Wi-Fi channel, while the FeelHippo AUV is connected with acoustic channel. The specification and the components are illustrated on this graph. The autonomous buoy are represented on this slide with main characteristics. Then we install the objects on the Italian basin. Then we estimate the position with the distance. These are the results. Over total detection of 61, only 2 wrong detection are found with the average distance error of 0.73 meter. To conclude our presentation, in the introduction, we have discussed on the FLS supply position estimate, which uses the NED frame with AUV position models, the estimate with a Gaussian density function. Then for the explanation, we had explained on the mathematical notation, simulation results, and experimental results with AUB for validating this PMHA FLS position estimation scheme is valid. For conclusion, the position estimate along with object classification with a deep learning model served as a key predicates in the PMHA algorithm for effective world modeling. This is the reference slide. And thank you for listening my presentation. If you don't know any terms on the presentation, please refer to the supplemental data. Thank you again.